Okay, friends, we'll pick back up. Question that happened over the break was, oh, did I press record? Yes. Will the exams be similar to the quizzes and the problem sets? I believe that the quizzes and problem set questions are pretty closely aligned with each other. Most of the problem set questions that you see, you've encountered something similar on an in-class quiz. Those really do sort of summarize the key skills and concepts that you need to know. And most questions I will ask you will be answerable using some of those key concepts or quizzes. Now, you shouldn't expect to walk into the exam and see a carbon copy of a question you've had before in exactly the same detail. Because what we're going here is not for simple memorization of facts, but mastery of skills. So you could not know that a molecule, you could know nothing about chirality at all, but simply memorize that that molecule is chiral, and then you can answer the question on the test, is that molecule chiral? But you haven't learned as much as I'm going to expect you to learn, which is to see a new molecule that you haven't seen before, but answer, is it chiral? So it's going to be focused on skills. Now, what that means is there's going to be some uncertainty because you're going to see a molecule you haven't seen before. That's okay. Life is about experiencing things you haven't experienced before, but using the skills that you've developed to meet those challenges. And again, I'm not, if you were my children, I would say I am not trying to raise robots as children. I don't want you to just memorize facts. I want you to be able to handle new and challenging situations. So you can expect the exam to explore the same issues that we've talked about, but using an example you haven't seen before. If I were to write a study guide for the exam, it would literally just go by each quiz and each problem set. These are the concepts and skills you need to be able to do. And indications of what's important you can also get from what we've talked about in class. Yeah?
Will Monday's material be on the Tuesday test?
Will Monday's material be on the Tuesday test? Yes, we're going to continue with stereochemistry. Yeah. So that doesn't give you a huge amount of time to practice. The midterm exams are going to be in the range of 20 to 30 questions long, 150 points. The final will be 295 points. So if a midterm doesn't go well, there's still 2 more midterms and a final that counts a whole lot more. The goal here is to eventually get there, and if you struggle on the midterm, that's okay, because you can replace one of your midterm scores with your percentage score on the final. Now that sounds like, I didn't want you to get mixed up. I don't want to communicate the idea that sure, you can get, if you get 295 points on the midterm, then you get 200, on the final, you get 295 points on the midterm. That would be an awesome extra credit deal. That's not actually how it works. I just mean if you get 100% on the final, then I'll replace your lowest midterm score with 100% on the midterm. Does that make sense? So there's a little bit of redemption built in here. I'm trying to balance the desire to improve with the desire to not have something be so high stakes that it freaks you out. Yeah?
When does the exam close on Wednesday?
Exam closes at an end of closing time, testing center on Wednesday. Spring hours are different, so you got to pay attention to that. Yeah?
Will, like, the overall exam, if we all don't do that well, which hopefully we will do well, will they be curved?
Yeah, so what does curving mean? Interpretation of your score in an OChem class is challenging, in part because I start with the default cutoff. So you could say, oh, if I get better than a 93, then I'm definitely on track for an A. But historically, if you look at OChem classes, the grade cutoffs between A and A minus and B plus tend to be pretty close to 90%. But the cutoff between, say, B and B minus tends to be pretty close to the low 80s. The cutoffs in the C range tend to be quite a bit lower than the default. For example, if you get 68% on a midterm exam, you would be inclined to think, oh my gosh, I am failing. And I would tell you, you are not. You're actually doing way better than failing. You were in the C range. Failing in this class means getting like 40% of the points. And if you do all the quizzes and the problem sets, you're already well on your way to that. So so in that way, it's difficult for me to interpret your score. If it's in the 90s, that's easy. If it's in the 80s, that's probably some kind of B. If it's in the 70s and below, that's probably some kind of C, but it's a little bit difficult for me to say. So again, if you end up in the 60s somewhere, think, I wish I were doing better, but don't think all hell has broken loose and everything is lost, because that's not how it is. Okay? In general, you can sort of assess your performance by looking at the median score on the exam. That is the 50th percentile score. If that median score is in the mid to low 80s, that would indicate that the cutoffs in the B and A range are pretty close to what they say in the syllabus. If the median score is lower than the mid to low 80s, if it's in the mid or upper 70s, that'll mean the cutoffs in the B range will be a little bit lower. So it's really hard to say. If you want to come talk about it afterwards, I'm happy to do so, but that's sort of how it is. I don't assign letter grades to any exams. I do that at the very end of the semester. So none of us are going to know how that shapes out until we see the final exams, but I can try to give you a sense for how things are going to turn out. Okay, other questions? Okay, I was excited to learn this. I looked it up on Wikipedia, and if you look up soap film, it gives you this information. So do you remember what we said about what surfactant molecules do at air-water interfaces? We said that phospholipids will stick their polar head groups in water and their nonpolar groups out in air. So I just learned this. This is kind of cool. Where to do this? So for soap bubbles, you could probably figure this out. If you think about the soap bubble, they involve soap and they involve water. They involve an outside that is air and an inside that is air. And so what's thought actually happens is you have the polar head groups, and bubbles can be formed by phospholipids or by, as you know, fatty acids or single tail types of things. So I'm just going to do the sort of soap type of thing that normally forms a micelle. What happens is you have the soap film that makes the bubble has an inner channel of water, and you have polar molecules. You have the polar head groups. This is going to take forever. I should have illustrated this ahead of time, but I just barely learned about it. So what are you going to do? Come on. All right. Trying again more carefully. Copy, paste, copy, paste. Why is this taking so long? Okay, we're going to get exponential growth here. So 8, 16. Oops, we lost some. Paste. All right, now I'm irritated because it's not red. Okay, we're almost there. We lost everything. Okay, copy, paste, spin it around, boom. Okay, so this is the outside of the soap bubble. This is the inside of the soap bubble. Air in both places, non-polar tail sticking out into air, polar head group sticking into a thin layer of water, and it's sort of a reverse bilayer. And someone, where are you, came up to me in the interim and was like, "Oh, it's a surface tension." Right, it's a surface tension issue. Why the bubble forms a sphere? It's minimizing its surface area and stuff like that. But anyway. Therefore what? I don't know, but now you can blow bubbles and know about it, so. But yeah, I mean, that does illustrate it's predictable behavior, right? Of course you're gonna have the polar head group oriented towards where the water is. And of course you're gonna have the non-polar tails either together or sticking out into air if there's no other option. Again, it's an example of a hydrophobic effect. Okay, Also on chirality, so I made some models that are examples of what we were talking about. These carbons have 4 different things attached. My fingers are holding the blue spheres, and then you can see that these are mirror images of each other. What's in my right hand here is a reflection of what's in my left hand. You see that the red spheres are oriented towards each other. From your perspective, the white sphere is a wedge pointing at you, and the green sphere is a dash pointing away from you. The line between the carbon and the red sphere is in the plane of the page. The line between the carbon and the blue sphere is also in the plane of the page, but pointing downward. You agree that they're mirror images? Okay. And now we'll do the claw action on the one on the right. We can get the red and the blue things together, but we can't get the green and the white things together. Ever, 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 ever. Okay? This molecule is chiral. This molecule is chiral. These 2 molecules are enantiomers. And these 2 carbons are stereocenters. All right? All right, so now we need to talk about how you talk about molecules with stereocenters. For alkene diastereomers, we had E and Z, but for this molecule that we just made, our pretend molecule, they would both have the same IUPAC name, right? Bromochlorofluoromethane. They're both bromochlorofluoromethane. But they're 2 different molecules, so we need a stereochemical descriptor, a way to designate one enantiomer from the other. And the modern way of doing this is with the designations R and S. Yes? Yes, we are recording. All of that business about what's on the exam and all of the stuff that the folks watching at home can't see because I was showing you these models, yeah, we got all that audio. All right. So let's talk about how to distinguish between these 2 enantiomers in terms of naming them. All right? We'll go down here. I'll paste them again. The first thing you're going to do is to redraw the molecule, and we're going to tip the molecule back on the hydrogen. So we're going to push back on the hydrogen and tip that molecule back into the page. All right, so what's the molecule going to look like when we do that? If we tip the hydrogen back, the fluorine ends up where the hydrogen was. Chloro is still here. Bromo ends up here, and now hydrogen is here. You see how we did that? So from your perspective, this is H. Sorry. Sorry. From your perspective, this is H. We're doing the molecule on the right. My right, your left. Oh, this is really not working. Yeah, so this is H, this is Cl, the red one is bromo, and the blue one is fluoro. We tip the hydrogen back. Fluoro comes up here, hydrogen comes up here, bromo rotates forward. Got it? Okay. We can do the same with our molecule on the right. We'll tip the hydrogen back. Fluoro comes up here. Chloro ends up here. Bromo comes forward, and hydrogen's in the back. If what I just did, that sort of manipulation of molecule shape on page is difficult for you, you should practice with the model set. Build something like this and say, what happens if I tip it over? What does it look like? Then redraw it. Okay? All right, now that we've done that, we're going to assign priority to each of the 4 atoms that are attached to the carbon in exactly the same way that we did for E versus Z. We'll first ask, are the atoms the same or are they different? And if they're different, then the heaviest atom is the highest priority and the lightest atom is the weakest priority. If they are the same kind of atom, we'll consider what they're bonded to, that tiebreaker procedure. This example's easy. Bromo is heaviest, so that's priority 1. Chloro is next, priority 2. Fluoro's priority 3, and hydrogen is priority 4. Now, I already knew that hydrogen was priority 4, and I purposefully oriented that priority 4 group to be a wedge going away from us. Okay? Questions about what we just did, assigning priority to the atoms? We'll do tons more examples of this and you'll have time to practice, but here it's pretty easy. Bromo, chloro, fluoro, 1, 2, and 3. Yeah?
So rotating it is just so you're able to distinguish the priority, or why are we doing that?
I rotated it. You could have distinguished the priority without rotating it. That would have been 4, 1, 2, and 3.
Yeah.
To do what I'm about to show you, you need the hydrogen either oriented away from you. The preferred position is to have the hydrogen oriented away from you. You can have it oriented towards you, but in the plane of the page, not so great.
Okay.
You gotta have one or the other. I'll teach you the procedure for when hydrogen's pointing towards you, I'm sorry, away from you, and then I'll show you a really simple adjustment when it's not, okay? So, you orient the highest priority functional group. Oh, I'm so sorry. That is absolutely wrong way to put it. You orient the lowest priority group, and understand that what I just did was mix up two things that I shouldn't have done. Priority assignments for stereochemistry have nothing to do with IUPAC highest priority functional group rules. It's just an atom by atom weight comparison. We orient the lowest priority group away from us, and then we draw an arrow from 1 to 2, from 2 to 3, and from 3 back to 1. And then we ask ourselves, is the direction of those arrows clockwise or counterclockwise? So that's counterclockwise, right? You guys know clockwise and counterclockwise? Okay, good. Don't feel insulted. I don't know what you know. Besides, people like hearing things they know. It makes them feel smart. I tell my children this all the time, and they're like, Dad, we know. Anyway, that never happens. If, when we do that, it is clockwise, and when the lowest priority group is oriented away from us, we will, if it's counterclockwise and the lowest priority group is oriented away from us, we will say that the configuration of that stereo center is S. You'll see that in the enantiomer, if we do the same analysis, drawing from 1 to 2, 2 to 3, 3 back to 1, it is the arrows point clockwise, and so we will call that R. R and S. These come from either Greek or Latin, I'm not sure. Rectus meaning right, and S meaning, S is for sinister, which it's unfortunate that this is in our language, but actually sinister is either Latin or Greek for left. And so I guess that we can conclude from that left-handed people are evil. Is that what we... No. In any case, that's the language that's sort of stuck. I don't know why it's that way, but that's where R and S come from. Yes?
What about if like fluorine and chlorine were swapped in their orient, like where they were, and so the 2 was at the top and 3 was down more to the left? I'm looking at the wall.
So if we started here and you switched the place of chlorine and fluorine,
Yeah.
you would switch from S to R and you would have made this enantiomer. So and that's actually a nice way of summarizing what we've learned so far. The difference between 2 enantiomers is 2 of the groups are swapped in their locations. Yep. So this would be S bromo, chloro, fluoromethane on the left, and on the right would be R bromo, chloro, fluoromethane. Okay? Let's do another simple example. here is an alcohol. Does the alcohol have a stereocenter in it? Which carbon is it? Carbon 2, the one that's attached to the oxygen. Okay. Let's assign priority so we can see what the configuration is. The hydrogen's pointing away from us. So, and the 4 groups that are attached to the carbon are hydrogen, carbon, carbon, and oxygen. So we know right away that hydrogen is priority group 4, and because oxygen's heavier than carbon, we know that oxygen's priority group 1. However, for the remaining 2, they're both carbons, and that's a tie. So what is the appropriate tie-breaking procedure? See what they're bonded to. Write it out in order of heaviness. So this carbon is bonded twice to carbons and twice to hydrogens. This one is bonded once to carbon and 3 times to hydrogen. We go down the list until we find a difference. We find a difference. That one is priority group 2. This one's priority group 3. See how that works? Okay, 1 to 2, 2 to 3, 3 back to 1. That is clockwise. So this stereocenter is what configuration? R. Now, let's draw the enantiomer. You can do this in multiple ways now. One way would be to do the mirror image, but another simple way is to draw the molecule in exactly the same orientation, except you switch the dash and wedgeness of of 2 groups, the oxygen and the hydrogen. To demonstrate that these 2 are enantiomers, let me do the pancake flip on this molecule. And if we do that, you would see that sorry, I'm not doing it very well in my head. We would end up with this. The triple lines there means these 2 are equal to each other by this pancake flip, and you see how this is a mirror image of that. Now let's suppose we're in the situation where we've easily assigned priority groups, but unfortunately, the lowest priority group is in the front, not in the back. We draw from 1 to 2, 2 to 3, 3 to 1. It looks like that is clockwise. But we're not going to assign R. We're instead going to switch the rule and assign S. So if priority 4 group is in front, then clockwise means S and counterclockwise means R. If priority 4 group is in back, clockwise means R and counterclockwise means S. The reason this works, it's kind of confusing to do it, but imagine stand with a friend and have the friend say, I'm rotating my finger counterclockwise, and then you look at it and it looks like what? Here I'm going clockwise for me, but what does it look to you? Yeah, exactly. Front, back changes clockwise to counterclockwise. So it's like, yeah, it's kind of hard to... You do it from the bottom and then go up. That's easier to do it. Okay. Right. So if the priority 4 group isn't in the, if it isn't in the back, if it's in the front, still do the same clockwise, counterclockwise thing, but remember to switch the rule. All right? So let's do a few quiz problems, shall we? We're now good to, I guess one other thing I should say. Let me point out that enantiomers have opposite configuration at all stereocenters. Okay? So if I didn't know that these 2 were mirror images of each other, if I observed that they had opposite configuration at their stereocenter, that would help me conclude that they're enantiomers of each other. All right, so go to question 2 on your quiz. And first, let's find the stereo centers in these molecules. Okay, so look at that first one. Where are the stereo centers? Remember, a stereo center is an sp3 carbon. Go ahead.
Is it where the methyl group is kind of goes in the page right next to the name?
There?
Yeah.
Yep. How can you tell that's a stereo center?
Because there's a hydrogen, carbon, and nitrogen in that double bond.
Right, so it may help you to draw in at least some of the hydrogens that are implied but not shown. That is an sp3 carbon attached to 1, 2, 3, 4 different things. These two carbons are different, right? That one's bonded to a carbonyl oxygen. This one's just a CH2 group, okay? Where's the other stereo center in the molecule? To the right of the NH, good. Here's the other one. Again, you can tell it's a stereo center because it's attached to 4 different things. Any other stereo centers in the molecule? Is that a stereo center?
No.
It's an sp3 carbon. Why isn't it a stereo center? Two of the same group. Good. You were not deceived. Is this a stereo center? Why not? 2 hydrogens. Good. Is that a stereo center? Why not? It's not sp3 hybridized. Good. Okay. Let's assign R versus S configuration here. I'm looking nitrogen, carbon, carbon, hydrogen. So which is priority group 1 and which is 4? Nitrogen's 1 because nitrogen's heavier than carbon. Which one's 4? Hydrogen. Good. Now among the 2 carbons, it's a tie. So what are they bonded to? How about this one? 2 carbons and 2 hydrogens. How about this one? What's it bonded to? In order of heaviness. 2 bonds to oxygen, a nitrogen, and a carbon. Oxygen versus carbon. Oxygen wins. That's 2 and then 3. So now let's draw the arrows. 1 to 2, 2 to 3, 3 back to 1. That is clockwise or counterclockwise? Clockwise, but priority group 4 is up, so we switch it. That stereo center is what? S. Good. All right, now do the other one. Getting there? Any questions? Okay, compare your answer with a friend if you got something. Okay, did anybody come to different conclusions? Got any discrepancies? If so, don't give up lightly. We want to make sure we understand the issues here. Okay, go ahead.
So are we just worried about the next thing it's connected to and not necessarily, like on this one, it's connected to the whole thing above, so I feel like it would have more weight than
Uh-huh.
three oxygens. But are we just worried about the next thing that the carbon?
Yeah, you're only, for the comparison between these two, you are exclusively worried about what it's bonded to. That atom, not the rest of the stuff. We will go out there if we have to, but not until there's a tie. Yeah?
I was just wondering, so if we were supposed to assign things, how would you assign the in like a name?
Oh, I would not give this an IUPAC name, but you would, if you did, you would put a, supposing we started at this end, 1, 2, 3, 4, 5, we would say 2, at the beginning in parentheses, we'd say 2 S or R, whatever it is, and then 5 S or R, whatever it is. You got a conclusion here? What is it? It's S, that's correct. Now, this is group 4, this is group 1, this is group 2, this is group 3. 1 to 2, 2 to 3, 3 back to 1. That is counterclockwise. Hold on, why is counterclockwise S here? Because group 4 is down away from you, and so therefore it is S. Good. Now, the quiz question 2 asks you to draw the enantiomer. There are 2 ways to do this. One is somewhat easier than the other. And the easy way to do it is simply to redraw the molecule in exactly the same orientation, only switch what was a dash before to a wedge, and then switch what was a wedge before to a dash. If a molecule is chiral, the way to draw its enantiomer is to draw opposite configuration at each and every stereocenter. So this would be the RR stereoisomer. Okay? And if you did the pancake flip on this one here, you'd see that it would then look like the mirror image of this one. These 2 molecules are enantiomers of each other. Okay? So with that, I think you're set. I want you to practice these. Yeah, go ahead.
If you were just to draw the mirror image, wouldn't that technically be the enantiomer?
Also, yep. So you can draw enantiomers 2 ways. You can draw the little dotted line and draw the mirror image, or you can change the dashes and the wedges. All right. We haven't yet really answered the question how to tell whether something is chiral or not. Or we have, in the sense that the basic way is draw the mirror image and see if it's the same thing. That's your fallback position. If you do that, you will never be deceived as long as you can reason through molecular shape. Now, there are some tricks, which I'll give you a clue. If the molecule has no stereocenters, for our purposes, it's going to be not chiral. Now, there are plenty of exceptions to that in reality, but you're not going to encounter them in this class, so we'll forget about them, okay? If a molecule has 1 and only 1, it must be chiral. If a molecule has 2 or more stereocenters, it might be, but you have to check. And you're looking out for molecules that are the same thing as their mirror images. Okay? So let's do the citrate example together before you leave. This is an important molecule in biology. Does citrate have a stereocenter? How about that carbon? Why is that not a stereocenter? Yeah, 2 identical things. CH2 bonded to a carboxylate here, CH2 bonded to a carboxylate there. So citrate is not chiral. How about isocitrate? How many stereocenters does it have? You sure? Is this a stereocenter? Yep, 4 different things. Carboxylic acid, OH, proton, and then carbon bonded to 3 things. Is that a stereocenter? Yep. That's a carboxylic acid, that's a CH2 group, that's a CH bonded to an OH, and there's a hydrogen on it. So yep, those are both stereocenters. Now, if there are 2 or more stereocenters, you have to check and see if it's chiral by seeing whether it might be the same thing as its mirror image. Now this one isn't. I'll tell you the answer that this one is chiral. You should check and verify that on me. Check on to see if that is. But the last thing I want to tell you is this molecule has stereocenters, but beware. Check and see by drawing the mirror image. You don't do it now because we're out of time, but check and see after class when you're working on this stuff. Is mesotartaric acid chiral? Don't look it up on the internet. Actually draw the mirror image and make the conclusion. Do that, and I'll see you on Monday. I'm